sacred institutions. Bedroom eyes, they called them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hi all, and welcome to this bonus episode of Physical Attraction. Now, I've talked about how we're moving to a bi-weekly schedule, but if I have a little bit of free time like I do today, then I'm perfectly happy to produce some content for you guys, and this is an article I've written that will hopefully be published soon on the Singularity University website. It's about the different kinds of solar panel, and I think it's an important topic for the world today. So it's called Splitting Sunbeams, and here we go. So occasionally in the world we observe empirical laws, the laws of experiment that seem to be spookily accurate. There's no theoretical reason why they should be obeyed, but they just happen to describe the world remarkably well. So perhaps the best example of this that's changed and will change the world the most is Moore's law. In its simplest form, what it states is that the number of transistors you can squeeze onto an integrated circuit in a computer doubles approximately every 18 months to 2 years. And that's been true for a very long time. And the result is an exponential increase in computing power. Exponential increases are a very powerful thing. For example, if all of you told one other person to listen to this show, then in 30 episodes, we'd have 1 trillion listeners. That's right, exactly 1 trillion listeners. Well, give or take a few billion anyway. And then if each of those trillion listeners donated just 1 cent, I would presumably have hundreds of billions of dollars and be richer than Jeff Bezos. And then I could give all of you guys a little bit of kickback for sending the listeners our way. But yes, exponential increases are a very powerful thing. If you're as old as me, you'll remember marvelling at 1.28 megabyte floppy disks as a kid. I remember thinking, that could hold all of the novels that you could ever write in .text form. Nowadays, people will hand out 2 gigabyte flash drives for free. Moore's law actually deals with the processing power of computers, rather than storage necessarily, although there's a similar rule that is obeyed for storage. We all know the factoid that there's as much processing power in a mobile phone today as there was in NASA's computers for calculating the moon landing. It's technically true, of course, but NASA computers needed to avoid the blue screen of death in the harsh reality of outer space, which your phone probably couldn't dream of doing. But of course, Moore's law, like all exponential increases, are eventually limited by just nature, just the limits of what can happen, the limits of validity of your equations, and the limits of availability of resources. So in the case of Moore's law, it's been rumoured to be demising for a long time, and they've often been greatly exaggerated. But it's not just a question of economics, although people have questioned whether the pace of R&D that's going on is really sustainable in computer chips. But see, the thing is, eventually you hit limits set by fundamental physics. There's a limit to the length scales that these components can actually be, which is set by obvious things like the size of an atom. I mean, if you're going to try and have a binary switch that's on or off, if you're saying you have to detect things on a below subatomic scale, you come into all kinds of quantum effects that make things a little bit weird. And you can't have a current, at least not an electrical current, that flows on a smaller scale than the particles that carry that current. Not with current technology. So with the technology that we're using at the moment, it seems likely that Moore's law will someday break down, although no one knows exactly when that will be. There is, however, a process that's been competing with Moore's law lately, one that will bring joy to any green warrior. The price of silicon-based solar cells has been falling off a cliff for years now. So, a long time ago, silicon solar cells were essentially only developed for use in outer space. There you have a premium on how much matter you can transport, because the heavier your rocket, the more fuel you need, the more expensive it is, and so on. So you can't send up a whole bunch of fossil fuels like we can use on Earth, which is basically why they developed solar panels in the first place. So in the 1970s, each watt of electricity generated by solar panels would cost you around $76, which is ridiculously expensive. So a watt of electricity, your light bulbs will be measured in kilowatts. A joule of energy is approximately the energy it takes to lift an apple from the floor, put it on a table. So a watt is a joule per second. So it's some energy, but your electrical appliances will consume that. So $76 for a watt is obviously not a very good deal. That was 1977. By 1987, that had dropped to $10 per watt. In 2015, it was 30 cents. This decline applies to solar energy prices from the grid, but the cost of installing your own system has been falling at a similar rate. So despite what various political figures have to say about it, soon enough the free market is going to dictate that new power plants should be solar power plants. It will be cheaper than coal and oil as they become more difficult to distract. It's that simple. So if you measure using the levelized cost of electricity, because you see there's this argument here. The thing with a solar panel farm is, once you've got it set up, as long as the sun's shining, it's producing power. With coal, oil, natural gas, you need to extract the resources, you've got to transport them, you've got to fuel it. So it's difficult to talk about costs in a way that is levelized, which is why they have the levelized cost of electricity. They're saying how much are the construction costs, how much are the fuel costs, how much does it cost to maintain and repair these things, that sort of thing. So you find that if you take this into account, the only thing cheaper to install in the UK in terms of levelized cost of electricity is onshore wind farms and natural gas power plants. And that's in the UK, where you wouldn't think that solar panels are going to be that effective. So at this rate, you're thinking, well, what about nuclear power, which a lot of people talk about us going back to? Well, the government has not been doing that well with that so far. The Hinkley Point C power station project, it's over a year behind schedule. It's £1.5 billion over budget. And it's already been outmoded due to this incredible drop in solar prices. Per megawatt hour of electricity that you generate, it's more expensive than a solar power plant would be. But of course, there are issues with renewable technology that explain why the trend in energy markets has been a new dash for gas and not a dash for renewables. In his brilliant book, Sustainable Energy Without the Hot Air, this book is available for free online, by the way, and if only one thing ever comes of me doing this show, I want it to be that as many people as possible read Sustainable Energy Without the Hot Air. It is brilliant. It's by the sadly missed David McKay, Fellow of the Royal Society of Cambridge, who died recently of cancer. And he explained what a Britain powered purely by renewable energy would look like, just by doing some simple calculations. The point that McKay is trying to make in Sustainable Energy Without the Hot Air is it's all very well saying we need more green power, we need less fossil fuels, energy efficiency savings are helpful, but if you don't have the numbers, it's not really clear what's going on. He wants to say, what would happen if we wanted to feed our current consumption with purely renewable means? What would that look like? And it turns out that we need a lot of renewable power. If we want to power the UK by solar panels alone, he estimated that we'd need to blanket 20% of the country in solar panels. That's all of the space on the islands of Great Britain and Northern Ireland. 20% of it in solar panels, which could be tricky to say the least. Of course, other sources like wind and hydroelectric power can help out. In reality, our renewable future, should we ever manage to get there, is going to depend on a complex mix of power sources that allow us to compensate for issues like the variability of power output from solar and wind, and a lot of people are focusing on battery storage because the wind doesn't always blow, the sun doesn't always shine. You have to have some way of maintaining a reliable supply of power. But one thing that certainly would help is if we had more efficient solar panels. So there's a simple fact that There's a good deal of radiation from the sun that falls on the Earth, but your current solar panels, commercially available ones, they range between about 10% efficiency and about 17% efficiency. That might sound quite low and depressing, but actually, if you look into the physics of it, you'll realise that 17% efficiency isn't far off the maximum. If you double the efficiency of solar panels, obviously you need half as much space to be covered by it. But here, scientists are struggling at fundamental physical limits, just like the technologists developing transistors are, as the battle to keep Moore's law going continues. So in the case of solar panels, it's something called the Shockley-Keyser limit. So how does a solar panel work? In its basic essence, you have a semiconductor, like silicon. It has N electrons in two energy bands. There's a low valence band and a high conduction band. So what you imagine is that a photon from the sun flies in and hits an electron in the low valence band. That gives it the energy and causes it to jump up into the conduction band. So now you've got this electron wiggling around, it's got more energy than all the ones in the valence band. But the issue is there's now differences in electron density. In some regions you have more electrons than others. And that means that there'll be an electromotive force. They're pushing on each other because there's a charge gradient. And that's what drives the current, the motion of charges, from which we essentially extract our electrical power. But there are limits to how much of the sun's energy we can extract. Here, you see, quantum mechanics is not our friend, because it insists that one electron can only absorb one photon, and only if it has enough energy to kick it into a different state. But the sun emits photons at many different energies. It's a whole black body spectrum. There's photons of many different energies that hit the solar panel. But the band gap energy, that is the energy you need to kick the electrons up a level, that's a fixed value for silicon. That's 1.1 electron volts. An electron volt is the amount of energy you get when an electron crosses through a voltage of 1 volt, and it's a good indication for energies on this sort of quantum scale. So a single photon of visible light is usually a couple of electron volts in energy. So there's this bandgap energy, that's 1.1 electron volts. If photons come in with less than this energy, say 0.5 or something, they can't excite an electron, and so they're effectively wasted. If photons come in with more than this energy, they'll dump all of their energy onto that electron, because of this quantum mechanical rule. One photon absorbed by one electron. Always. No half measures. So, if there is an electron that's hit by a 2 eV photon, 1.1 electron volts of that energy goes into jumping the bandgap. But the rest of it is thermal energy in the electron. The electron is moving quickly, effectively. But there's a big problem, because this energy is just dissipated into the solar panel, and it's difficult to extract. The electron collides with a whole bunch of things, and the energy is distributed, and it's lost as heat. It's no good. It heats up, as objects do in the sun, but it's not converting that energy into the electrical power we need. So when you take all of this into account, the upper limit of efficiency for traditional silicon solar cells is 32% of the solar energy that falls on them. Take factors like reflection from the surface of the solar panel and wires that block light into account, and this falls to around 24% for the area of the solar panel. So, despite all of the solar energy that's falling on the Earth, only 24% of it can be converted by silicon. So this can lead to a bit of confusion when you're marketing solar cells. If I say that a solar cell is 17% efficient, that sounds rubbish, doesn't it? But actually, 17 out of 24 is a pretty big fraction. You're getting pretty close to the limits of what the technology can do. And if you heard something was only 24% efficient, you might think, there's no point investing in this. In a few years' time, it'll be better, and we'll be able to, have a more efficient solar cell. But the actual fact is, 24% efficiency, that's getting towards the fundamental limits here. This efficiency has only been obtained through years of refinement. So what we're seeing with the Shockley-Keyser limit is a fundamental limit, something that can't be done. So how can we cheat the sun? One method is via tandem solar cells. So this idea, you have multiple solar cells joined together, made of multiple semiconducting materials, with different band gaps. So each layer of the solar cell harvests a different area of the sun's spectrum. So this technique sort of works. Currently available tandem cells can get you up to 44% efficiency under good conditions. But the issue is they're very, very expensive to manufacture. Getting the currents from each cell to constructively add up turns out to be a tricky problem in engineering. Because these cells are so expensive, they're basically what's used on satellites now. As we talked about for the initial development of solar cells, the key thing with satellites is you don't really care how expensive your electricity generator is, as long as it's light, and as long as it will work in outer space. So there are other ideas that are being investigated. One of them includes quantum dot solar cells. A quantum dot is like an artificial atom made out of semiconducting material. The size and shape of the semiconductor blob, which is on the nanoscale, determines its electrical properties. So with these, what you can do is set your own band gap. So we talked about how the natural band gap of silicon is 1.1 electron volts, and that means that a lot of photons end up being wasted. Well, it turns out that 1.1 electron volts is close, but not quite the same, as the peak in intensity from the sun. The peak in intensity from the sun is a little bit more. So if you tune the solar cell to be at exactly the same band gap as the peak in intensity from the sun, you can approach the Shockley-Keyser limit of 32%. There are other materials that might have these tunable properties where you can change the band gap to whatever you want. One of them is this miracle crystalline structure called a Perovskite. The special crystalline structure of these Perovskite crystals can be manipulated to allow us to change the band gap. Since the band gap determines the type of light that a semiconductor will emit, as well as absorb, these materials can also allow us to produce more efficient LEDs across a range of different colours. And if you look up Perovskite LED, you'll see some incredibly bright, sort of multicoloured range things. There's very, very good Perovskite LEDs. Another area that's elicited a great deal of excitement is the so-called Singlet fission materials. These are a special kind of material that can split photons. Well, they don't actually split them. Here's what happens instead. They absorb a high-energy photon. Then you have an electron-hole pair. So an electron is excited and it leaves a gap. The gap behaves like a positive charge, while the electron is negative, and they're bound together because of that electric force between the positive and negative charge. That pair travels along, and then it splits into two pairs by interacting with some other electrons. Then each of those pairs emit a photon. So you see what's happened here is that you've effectively converted the high energy photon, whose energy might have been wasted, into two lower energy photons, which could then theoretically be absorbed by a conventional solar panel underneath. So this offers a dream eventual application. If you have the right kind of singlet fission material, maybe you could just paint it onto a traditional solar cell and watch its efficiency climb up. But in practice, of course, we need to investigate much more about these materials before this type of technology can be imagined. And after the university research scientists are done with them, there'll need to be a lot more technological development before you can buy them in the shops. It's exciting to think that we're constantly finding new ways to push the boundaries of physics and do things that were previously thought to be impossible. In the case of the renewable energy, it may well have to be necessary that we do find limits past the limits if we want to continue being impossible creatures on a habitable rock. So there we go, that's my sweet little article about renewable energy, and it's going up hopefully next week sometime on Singularity Hub. I'm trying to write at the moment something very ambitious, which is going to be an update of the calculations that McKay does in sustainable energy without the hot air, as a sort of tribute to the great man, I guess you'd say. So yeah, thoughts, opinions, anything like that? Be very good to hear from you all. Remember all that you can like us and review us on iTunes. That would be great. I'm thinking that the next people who review us on iTunes I'm going to mention at the end of the show, so you're going to get your name in lights. And if I can get enough reviews that it's reasonable to do this, I might do a prize draw. That would be fun, wouldn't it? Until next time, stay safe.
Pornographic tastes, a Marquis de Sade would have regarded as a peer. Hi, folks. Want to hear something funny? I'm cursed. An abnormal sexual